Today we're going to be looking at a very heavily requested Alan Becker video. Animation versus physics. As a nuclear engineer, I know quite a bit about physics, so this should be quite interesting. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's get right into it. Well, starting off in space is good for a physics video. Oh, landed on something. Ooh. The first noteworthy difference between this and animation versus math, units. Because physics has units. Math, it would just be 4.6, or maybe some variable. But here, 4.6 meters. One of the important distinctions. And they defined it as distance. Velocity arrows. Velocity being speed with direction. Oh, that's cool. And displacement, distance with direction. He notices. Velocity. Another velocity relative to another velocity, which is acceleration. And you're adding them up. Constant speed. Oh. Deceleration. Oh, and he got hit in the head. So gravity and mass now. Kilogram. Mass. Force. Mass times acceleration. So what's interesting is work in physics is a force exerted over some displacement or distance. So if you're sitting around in your office working at a cubicle, are you really doing any work? And power being work over some unit of time. Nice trajectory. Ooh, what's this? Up friction, so they got some friction there, and that's got almost no friction on the ice. Balancing forces, they just get bigger. Rope? What's that? Star? Gonna use the rope for balance. Oh, nice angular momentum. Yep. Just spin it around. Yeah, momentum is just mass times velocity, and angular momentum is just that with rotation. There we go. We know he's 50 kilograms. There we go. Momentum and ice skating. Uh-oh. Incoming collision. Nice. Conservation of momentum in effect. Note that weird things happen when you get to different scales, though, but it'll work on this little ice collision example. There it goes. Ooh, potential to kinetic, and then back to potential again. And that was just enough to get it there. Just enough. See what he does. Oh, I love that animation. Potentials to kinetic, back to potential. But that wasn't enough. Just slides all the way back. There you go, that should give him just enough. Oh, a little more. Just random floating rocket. Okay. What's he gonna do? Gonna try to get there using the big ball. Ooh, torque. Just how angular momentum is the rotational analog of linear momentum, this is that of a force. I'm gonna use torque to get up to the rocket, it looks like. It's just floating there. Oh, and gravity's gonna go away. So that's interesting. So this planet is pretty small, has fairly high gravity, and yet he was able to slingshot himself around a tree, give himself enough force to escape and get up to this rocket. Can't recommend trying to do that in real life. There he is. Thrust. The velocity is going to keep going up as long as that rocket's on. Heading to a star or a planet. Gotta have cowboy hat. There you go. More thrust. Ooh, the Lorentz factor. So, interesting things happen when you approach the speed of light. It's this multiplication factor that causes your kinetic energy and your momentum to go way, way up as you get closer to the speed of light, asymptotically. You'll see on their little graph they provided right there. Beta is your fraction of the speed of light. At 104 meters per second, he's nowhere close to that. Speaking of light, shadows. And there's the speed of light right there. Interesting that the speed of light is actually an exact definition, like the definition of a meter corresponds to the unit for the speed of light. So it's an exact measurement, even though it's kind of hard to actually measure that. Specifically, you can't measure the one-way speed of light. Ooh, all the colors! That's the electromagnetic spectrum. All this is radiation, by the way. So yes, colors are just types of radiation that is picked up by radiation detectors, those being your eyeballs, of a certain wavelength. Red being longer, blue being shorter. Infrared being way long, ultraviolet being way short. Coming up on some planet, okay. Oh, he's gonna slingshot around him, isn't he? Yes, the speed boost. Now he's getting on up there. Oh, you're seeing the relative velocities of the planets. There you go. Getting bigger. Ooh, here comes a star. Does he have enough? Nope, he's on a collision course. What? By the way, this would never work in real life. Even if he was super strong and can generate so much thrust with that cowboy hat. There's no atmosphere in space, so nothing to give him that additional thrust. Looks like it's working here, though, in this universe. Getting on up there. 1% of the speed of light. Not quite relativistic. You're not going to notice many of the effects just yet. It's a magnet. That's a very strong magnet. By the way, magnetic force, way stronger than gravity. The rod. Ooh, okay. A bunch of magnets in a row. It's gonna use that to accelerate. Okay, he's inducing a field. And what a solenoid. Solenoids are pretty cool. They're actually used quite commonly at nuclear power plants, as well as any power plant. Basically, a solenoid is a device. You run current through a wire, you wrap it around real tight, kind of like a slinky. You're going to need a lot more turns than this, by the way. He's just wrapping a bit of steel around his rocket. And basically what a solenoid does is it converts that magnetic energy into mechanical energy. I mainly think of it in terms of opening a valve. A lot of solenoid operating valves at a power plant. But I guess you could wrap one around your rocket and go through a bunch of magnets. Now it's a magnet now. So basically a big mass driver or coil gun, or use magnets to propel a projectile. Here we go. A lot of magnets. All right, 80% of the speed of light, you're gonna notice some stuff. Like time dilation. Now he's looking at all the stuff in space. By the way, if you're going that fast, everything is going to be so bright, you're not really going to be able to see anything. Time and space dilation, yep. Galaxies. Oh, the quasar from the... All right, now we got the higher energy light, the gammas and X-rays, radiation, ionizing radiation at this point. Enough energy to strip electrons off of atoms. But yeah, people talk about gamma radiation being super scary. It's just high energy light. Ooh, the Doppler effect. Now that's a real interesting one. So you're probably familiar with the Doppler effect, like say an ambulance coming towards you. It has a higher pitch when it comes toward you, and then when it passes you, it goes away from you. It's at a lower pitch. Same thing happens with light. So you notice the blue shift, it says blue shift in front of the guy. You're going towards it, it's going to look blue, so things with a shorter wavelength. And then when it's coming away from you, it's going to have a longer wavelength, red shifting. Now this is a very important thing that is regularly monitored by nuclear reactor operators, nuclear engineers, because this is a key component as to how the fission process works. Because you need to accommodate for that when a neutron is approaching a target uranium nucleus. Those effects are noticeable. If the nucleus is coming towards it or going away from it, that difference affects the probability of whether or not the neutron will cause a fission. Approaching the black hole. The accretion disk, yep. So he's close to the speed of light, but can't escape that. The singularity, theoretical point of infinite mass that... it normally doesn't throw apples at you, but okay. What is that apple? Why is he going towards it? So what's interesting about a black hole is if you're like sitting back at a safe distance watching this crazy guy go into it, you're never actually going to see him go all the way in because of that whole light not being able to escape a black hole thing. You're going to see him go, suddenly stop, and then he's just going to get suddenly more and more redshifted and then just disappear. It's weird. There it goes. Light. Okay, so it showed those lines of gravity. What's interesting is as you go towards a black hole, the effect of gravity on different parts of the person, the rocket, is different on, say, the front versus the back. Now, that's true everywhere, but it's not noticeable on Earth because the effect of gravity is about the same on your feet as it is on your head. But if you're in a black hole and you're approaching that singularity, the effect on the feet is going to be a lot relative to the effect on the head, to the point where you get spaghettified and stretched to the point where you'll eventually just get pulled apart. Things getting red-shifted as they move away from you. Yep. There's that apple again. Just bouncing off of that singularity? What? Now here comes the spaghettification. Yep. Whoa, did he just go through it? Yeah, the black hole's being... Yeah, the black hole's being spaghettified. Or, I'm sorry, the apple is being torn apart. So he's shrinking. The plant cells. DNA strands. Gotta go all the way down to atoms, quarks. Yep. Neutrinos. World sheets. Well, he survived. In reality, he probably would have been dead before the apple did, but maybe there's something a little out of the ordinary about him. Then again, we don't really know what goes on inside the black hole. Okay, yeah, you're seeing the effects on time. Future, past. Oh, and there he is. Is that past him or alternate universe him? Either way, he's got no cowboy hat. Maybe cowboy hats don't exist in this universe. Everything's all messed up. It's very fluid and floaty, wherever they're at. There's that apple. It survived. Whoa. Oh, it's one of them little compacted pocket dimension thingies. I don't know a whole lot about that. Maybe someone can help me down below in the comments. What is that? Oh, it's a wormhole. Okay. Well, that's cool. Now they're seeing the past. Oh. These guys. They were the intervention people from the future. Kind of like in that movie Interstellar, where the guy goes into a black hole and now he does things to communicate with people from the past. That's really cool. Bet they also set up the rocket and the crazy magnetic fields so they can get there. I think that's a stable time loop. Here comes the rope. Open and close strings. Okay. closed strings to make a ball and the open one to make a lasso. Really, that's all it is. A closed string has endpoints and an open one does not. It's that simple. And here comes the rocket. Interesting, so entanglement is when a pair of particles are attached to each other despite being in very different parts of the universe. It could be a pair of protons, for instance. I've never seen it with a rocket, though, but these people might have access to some sort of extra-dimensional super technology, so, why not? Spinning it up. Oh, it's gonna suck everything in, isn't it? Yep. Ooh. So right there, the Hawking radiation, that's kind of a weird one, because you have these virtual particles that show up around the edge of a black hole. One of them goes in, like you'd expect anything to fall into a black hole. But then the other one actually leaves, so that black hole loses some of its mass energy. And that is what eventually kills black holes, those little virtual particles. Talk about death of a thousand cuts over the course of a Google years to take down a supermassive black hole. There goes the tree. So the apple formed that tree. That apple. That confirms what I thought earlier. They're the ones that have been given all this stuff. The flashlights, the magnets. Yep. Ooh, the solar system. Forgot about the solar system. That is so cool. Oh, and here they see him. They were the practical jokers that got him with the apple from the black hole. That's hilarious. The mode selector switch on the wormhole, so it moves on. Different universe type. And there he goes. Wow, that was quite the ride, and such an entertaining way to do physics. Again, they should show this in every physics class. I would have loved this so much, and even people that were just kind of on the fence and wanting to learn about physics, I'm sure you would have gotten a lot more of those people engaged. Thanks so much for the recommendation. This was awesome, and thank you for watching. I'll see you next time.